Okay, so by now you've had the chance to see how L'Hopital's rule can be very helpful to us when we are evaluating limits that give us an indeterminate form. This last example here that we're going to look at, I'm going to do a comparison so that we can compare what happens sometimes when we have square roots, and L'Hopital's rule kind of gets us in a bind. So let's go ahead and look at the example first on the left. If we try to do a direct substitution, we'll have 3 times infinity on the top, which will give us infinity, and then infinity plus 3 square rooted, which will give us infinity as well. So I'm going to apply L'Hopital's rule. Now before I do, I might want to rewrite this as the limit as x approaches infinity of 3x divided by x plus 3 raised to the 1/2 power. Because we can, as we've seen before, it's a lot easier to take a derivative if we can see the exponents that are on it. So now I'm going to go ahead and use L'Hopital's rule, and notice that I do write the LR. That's just to let me know I'm using L'Hopital's rule. And L'Hopital's rule says if we get an indeterminate form, this will be equal to the limit as x approaches infinity of the derivative of the top, which is 3, divided by the derivative of the bottom. When I take the derivative of the bottom, that's a chain rule. So we start by putting the 1/2 down in front. We then take that x plus 3 and raise it to the 1/2 minus 1, or negative 1/2 power, times the derivative of what's inside, which of course is just a 1. And so here we've got a little cleaning up to do. Let's see what happens to this. This is going to be the limit as x approaches infinity. Now the 3 can stay where it is. This 1/2 needs to be, it's a fraction, so we're going to flip it and multiply it. So that's going to put a 2/1 on it. And of course, this part here is to a negative exponent, so that's going to come up to the top as an x plus 3 raised to the 1/2 power. And of course, that's just over 1. So we get here that this is equal to the limit as x approaches infinity of 6 times the square root of x plus 3. And of course, when plugging in infinity for this, we get infinity, no longer an indeterminate form. So L'Hopital's rule works out quite nicely for us. Now, if we look at the second example, we're going to see a case where L'Hopital's rule causes us a little bit of a problem. And the reason for this, I'm going to tell you that up front, is because of the x squared sitting underneath that square root. And as a matter of fact, if you have a root that has an exponent in it greater than 1, you're going to see the same problem that I'm about to show you. When we look at this, of course, we once again see infinity over infinity, and I will one more time just rewrite this as the limit as x approaches infinity of 3x, of course, divided by x squared plus 3 raised to the 1/2. And now I'll go ahead and apply L'Hopital's rule. And in applying L'Hopital's rule, that simply means we're going to take the limit as x approaches infinity. We'll take the derivative of the top, which is 3, and then we'll take the derivative of the bottom. Once again, a chain rule. The 1/2 is going to come down in front. We'll then take the x squared plus 3 and raise it to the 1/2 minus 1, or negative 1/2 power, times the derivative of what's inside, which in this case is going to give us a 2x. Now, this 1/2 and this 2x are going to cancel out, so let me rewrite and clean up what I have here. This is going to then give me the limit as x approaches infinity of the following. I will have 3 times x squared plus 3 raised to the 1/2 over x. And you can see why this happens. The 3 stays where it is. This x squared plus 3 to the negative 1/2 is going to come up top as a 1/2, and the 1/2 and the 2 cancel, but I still was stuck with an x at the bottom. Now, let's go ahead and try a direct substitution. And of course, once again, I am going to get infinity on the top and infinity on the bottom. So I will once again apply L'Hopital's rule. And when I do, I'm going to get the limit as x approaches infinity of the following. Starting by taking the derivative of the top, of course the 3 just carries down, and then we take the derivative of this piece using our chain rule. That's going to be 1/2 times x squared plus 3 raised to the negative 1/2 times the derivative of what's inside, which is again 2x. And we're going to divide that by the derivative of the bottom, which is 1. So then the 1/2 and the 2 on top are going to cancel out. And when we clean this thing up, we're going to get the limit as x approaches infinity. The 3 is going to stay where it is, and so is the x. But this square root of x squared plus 3 is going to come back down to the bottom as an x squared plus 3 raised to the 1/2. So notice what has happened here. Every time we apply L'Hopital's rule, we do wind up decreasing. For example, look, starting here, notice we decreased or got rid of an x in the top. But when we took the derivative of the bottom, unlike taking it the other time, when we took the derivative of the bottom here, we just moved that square root up to the top. But because the inside derivative was 1, we didn't add any new x's, and so we were able to get rid of an x completely on the bottom and or top of that equation. However, when I have a chain rule and I have something bigger than an x on the inside, again, taking the derivative of the top gets rid of the x, but when I take the derivative of the bottom, I not only move the square root, but I create a whole new x. That x then goes at the bottom, the square root goes on the top, and I apply L'Hopital's rule again. Notice that the bottom x goes away, but when I take the derivative of the top using the chain rule, and I go to take the derivative of what's inside, I produce another x. That x stays on top, the square root comes in on the bottom, so that each and every single time we were to apply L'Hopital's rule to this, we would just keep moving that square root back and forth from the top to the bottom and producing an x on the alternate side, meaning that L'Hopital's rule is never going to get us to a result on this. So what is it we have to do on this one? Well, I'll show you. Let's go ahead and look at this one more time and take the limit as x approaches infinity of 3x divided by the square root of x squared plus 3. And if we remember back when we did limits the first time, of course, still getting infinity over infinity is an indeterminate form, but we know L'Hopital's rule won't work here. So what did we do instead? Well, we divided by the highest power of x. Highest, if I can spell here, power of x. And that means simply dividing each and every term by the highest power of x. Well, the highest power of x is simply an x. However, watch how I'm going to do this. I'm going to rewrite this as the limit as x approaches infinity of 3x divided by x. That's dividing the top term by x. But when I divide this bottom term, instead of writing it as an x, I'm going to write it as the square root of x squared. Notice that the square root of x squared is still x. However, what I'm going to need to do is to try to find a way to combine that into some kind of single term and to try to find a way to combine that into some single term. Well, an x with an x will cancel, so the top will clean up nicely like it is. But you cannot just divide this bottom by x and then come inside that square root and do your canceling. But by putting both of these under a square root, I get to put them under a single square root. So this becomes the square root of x squared plus 3 over x squared. And the property I'm using here is that the square root of a over the square root of b will be equal to the square root of a over b. And that's very true. You could have not taken the square root of x squared plus 3 and divided those terms by x by doing any kind of canceling, because there's a function here on the outside. And you can't go into that function. But if they're both the same function, I can put them in the same thing. So what does this allow me to do? Well, then this allows me to put that x squared, square root of x squared, together with this other one. I'll split it now into two separate terms. So I get the square root of x squared over x squared plus 3 over x squared. And I can actually do some canceling on this. This will become the limit. Sorry about this. My camera's a little bit off here, so bear with me for a minute. This will become the limit as x approaches infinity of 3 divided by the square root of x squared divided by x squared is 1 plus 3 over x squared. And then what happens when we put infinity into the denominator of any fraction? That fraction goes to 0. So we simply get 3 over the square root of 1, which is 3. So again, here was a case where L'Hopital's rule would not work because we just kept reproducing tops and bottoms and never got rid of anything, but we simply came in and divided by the highest power of x.